Hi there, welcome back to our video lecture in ENSC107, and in this video we'll be doing some more problems on pressure variation with depth or elevations. Now, instead of doing the same problem that I have mentioned in the previous video, I'd rather change the problem and you will have this one. Okay, it's basically or essentially it's the same. Now the problem says that an open tank contains 5.8 meters of water, and on top of that is a 3.2 meter depth of kerosene, and the specific weight is 8 kilonewton per meter cube. The problem says find the pressure at the interface and at the bottom of the tank. Okay, so the problem says we have an open tank, so meaning that the top surface is exposed to atmospheric pressure. Okay, so if it's in atmospheric pressure, then that's going to be 101.3 kPa. But with respect to gauge pressure measurement, this level right here, the atmospheric line, that would be a zero pressure for the gauge, right? So we have here a surface, and then we have an interface. Okay, so the reason why there's an interface is simply because there's a difference in the density of the fluids. So as you can see, the unit weight of the kerosene is lower than the unit weight of the water, and so that's why they can't mix. They can't mix completely. Okay, so we are asked to find what's the pressure right here. Okay, so let's say this is point A, and then what's the pressure, or let's just say 0.2. Then this one, what's the pressure here at the bottom. Okay, so now let's label, or let's include the dimensions, the height. So the height is 3.2, and that's in meter, and this one is this one is 5.8, and this one is, we'll just use this one, we'll just use the black ink pen, 5.8 meter, and this one is 3.2 meters. Okay, so if this is going to be our reference for the gauge, so let's say this is P sub 1, which is just 0. Okay, so if we analyze the problem, we can determine the pressure here, the pressure in this interface, by just applying the hydrostatic equations, where it is delta P is equal to the negative of the unit weight of the fluid times the difference of the depth. Okay, so if it's going downward, then that's going to be negative. Okay, so now let's write the solution. Okay, so now let's write solving for the pressure at the interface. At the interface. Okay, so let's apply the hydrostatic equations. That's delta P from point 1 to point 2 is equal to the negative of the unit weight of kerosene times the pressure difference, I mean the elevation difference. That's just delta Y from point 1 to point 2. Okay, so we'll write this down. P2 minus P1 is equal to negative 8 kilonewton per meter cube times this one, from point 2 to, from point 1 to point 2. But since this is delta, then you should be that should be the final minus the initial. Okay, so from this reference, right, this distance is, this point 2 is negative, right? So that's going to be negative 3.2 and then minus the initial, which is just 0, because that is your reference. Okay, so if we simplify this one, our pressure at point 1 with respect to the gauge pressure, that's going to be 0. So therefore our P sub 2 is equal to negative 8 kilonewton per meter cube, all right, times the negative of 3.2 meters. All right, so negative times negative, that cancels out, and that's why sometimes it's just simplified to just take the positive values right here. So instead of writing negative, just use positive, provided that the distance, your direction is going down. But if it's going up, then that's going to be negative right here. Okay, so if we do the math, what we get is 25.6 kPa. Right, so now let's solve. Since we now have the pressure in this point 2, then we can now solve for the pressure in point 3. Okay, so solving for the pressure at point 3. Okay, so again, we just apply the hydrostatic equations. That's delta P from point 2 to point 3. It's just negative of the fluid, which is water, times the delta Y, is the difference in the height from 2 to 3. Okay, so we just substitute all the values. That's 9.81. Right, so that's negative times again the negative, so that cancels out. This one would be 5.8 meters. Okay, and in this left side of the equation, we have P sub 3 minus P sub 2, right? But our P sub 2 is 25.6, right? So therefore, if we transpose this into the right hand side, what we get is P3 is equal to 25.6 plus that's in kPa, right, times this one, 9.81, that's in kilonewton per meter cube, times 5.8 meters. Okay, so by the way, this one should be plus right here. Okay, so if you transpose this to the right hand side, that's going to be P sub 2 plus this term right here. Okay, so now if you do the math, what you get is 82.45 kPa. Okay, so by the way, you would notice that this unit weight of water is written in terms in this value 9.81 instead of 9,810. It's simply because if this is the value that's in Newton per meter cube, so if you divide this by 1,000, what you get is 9.81 kilonewton per meter cube. Right, now we'll do another problem, but in this problem we'll have multiple fluids inside the container. Okay, the problem says in the figure shown, if the atmospheric pressure is 101.03 kPa and the absolute pressure at the bottom of the tank is 231.3 kPa, what is the specific gravity of the olive oil? Okay, so the setup is that we have a container, and that container, this container is open on top, meaning that it is exposed to the atmospheric pressure, and the first layer of fluid is SAE oil with an SG of 0.89 and a depth of 1.5 meters. Okay, so the second layer is water with an SG is equal to 1, that's 2.5 meters. Then 2.9 for the next layer of fluid, which is olive oil, but we don't have the specific gravity, and that's because that's what we are going to solve for. And then the last layer is the mercury with an SG of 13.6, 0.4. Right now, if you can see, that we have this, let's say we have this sequence wherein those with SG that's less than the water, or let's say those fluid with the lowest SG is on top, while the fluid with a higher SG is at the bottom. Okay, so this is 13.6, and then this one we don't know, but most likely that will be greater than SG is equal to 1. And then we have on the top is the SAE oil with SG is equal to 0.89. Okay, so this one right here, we have pressure, atmospheric pressure, but if we convert that to gauge, this one would be 0. And here at the bottom, what's given is the absolute, so basically we have to convert this to gauge pressure. Okay, so now let's solve for the gauge pressure at the bottom of the tank. So solve for the gauge pressure at the bottom of the tank. Okay, so our relationship is that P absolute is equal to P atmospheric, okay, plus P gauge. Now this one is given, this atmospheric is given, and then the P gauge is the unknowns. Therefore, P gauge just simply P absolute minus P atmospheric. And then the P absolute is 231.3 kPa minus 101.03 kPa, and that's gonna be 130.27 kPa. Okay, so let's solve now for the pressure. So we'll start from here, and then we'll find the pressures at the interface. Solving for the pressure at the interfaces. Okay, and then our equation is just the hydrostatic equation, which is just delta Y. So that's just simply P final minus P initial. Then we'll take the positive sign simply because we are going downwards. Okay, and then our height right here. So let's just write H. Okay, and therefore if we want to find the final, so P final is just P initial plus this, let's say plus H. Okay, so that's going to be our working equation. Now let's solve for, let's write, let's assign points right here. So let's say this is point 1, this is point 2, this is 3, 4, and then this is this is 5. Right, so for P sub 2 is equal to P sub 1 plus the unit weight. Right, that's the unit weight of SAE oil, and the unit weight is just simply right, so let's just write down the equation first. That's SG, then this is your substance or fluid, divided by the reference fluid, which is since these are all liquids, then this will be water. Therefore, our equation for this would be Sg times the unit weight of water. Let's go to the unit weight of the substance, and this one is 9,810 or 9.81 kilonewton per meter cube. Right, so therefore now let's solve for P sub 2 is equal to P sub 1 plus the unit weight of the substance, which is just the Sg 0.89 times 9.881 kilonewton per meter cube times the height, which is 1.5. At this one, P sub 1, since that's our reference line, which is the atmospheric line, and with respect to the gauge pressure measurement, this one is just 0. Okay, so this one is 13.09 kPa. Now for the P sub 3, it's just simply equal to P sub 2. Right, so now we are solving this portion, the water layer, and we are solving this point 3. So point 3 is equal to point 2, right, plus the unit weight of water, which is just 9.81 kilonewton per meter cube, times the height, which is 2.5 meters. Okay, and we get 37.615 kPa. Okay, what else? Now let's solve for, okay, in this layer, the olive oil layer, we don't have the Sg, and therefore we cannot solve for the pressure. So we'll skip for that. We'll skip that for now, and we'll move on to this one. Okay, so between 0.4 and 0.5, the pressure difference here. So that we can solve for 0.4. Okay, so P, the pressure at 0.5 is just equal to pressure at 0.4 plus the unit weight, Sg times the unit weight of water, which is just 13.6 times 9.81 times the height, which is 0.4 meters. Okay, so since we have this, actually, right, we have already solved this one, which is equal to 130.27. Therefore, what we're solving is the P sub 4. So if you do the math, you do the algebraic operations, what you get is 26.90 kPa. Okay, so now you have P sub 4. You have the pressure at 0.4, and you already have the pressure at 0.3. So solving now for Sg of oil. Okay, so we have P sub 4 minus P sub 3. Okay, that's our delta P is equal to the unit weight of the oil times the height, which is 2.9, right? 2.9 meters. Okay, you have 0.4, you have the pressure at 0.4 and 0.3, and you have this, so therefore you can solve for the unit weight of the oil, which is just equal to 13.55. This is kilonewton per meter cube, and therefore SG is equal to the unit weight of the oil, which is 13.55 divided by 9.81, and what you get is 1.38. Okay, so that's one of the solution. Right, now let's do another method of solving this problem. Okay, so let's just say method number 2. Okay, so we can also write it in terms of summation because it just simply adds up. Then our equation for the hydrostatic equation is just simply this one. Right, so y, this gamma times the height. Right, so the gamma times the height per layer. Okay, this one, we'll just add it up. Okay, so from 0.5 delta P, from 0.5 to 0.1, that's going to be P5 minus P1 is just equal to by the way, this one is the specific gravity times the unit weight of water, right, and that's going to be your unit weight of substance. Okay, so for this one, for the first layer, we have 0.89, so 0.89, okay, this is it, times the 9.81, times 9.81, that's the kilonewton per meter cube, right, times the height, which is 1.5 meters. Right, so that's our first layer. Now we'll add this the second layer, which is the water. So the water is just simply 1 times 9.81 kilonewton per meter cube times the height of water, which is just 2.5 meters. Then the next one is SG, the olive oil. Since we don't have the SG, then we'll just write the symbol SG times 9.81 kilonewton per meter cube times 2.9 meters. And then lastly, what we'll get is 13.6 times 9.8 kilonewton per meter cube, right, times 0.4 meters. Right, so this will be our equation, and for 0.5 we have this value already because that's our pressure at the bottom of the tank, which is 130.27. so that's gonna be 130.27 minus our pressure on top, so minus 0, is equal to the sum of all this, which is just equal to 1.335 plus 2.5 plus 2.9 SG plus 5.44, and if you do the math, we get 1.38. Alright, so I guess we have enough problems already regarding the pressure variation with depth. Now in the next video we will be discussing our remaining topics on pressure variation with what do you call that, pressure variation in space, or let's say in the atmosphere. or maybe we can try, I think we still have time, then we'll just derive it here. Okay, so let's move on to our next topic, which is the pressure variation in the atmosphere. Okay, so we already derived the equation delta P is equal to negative the unit weight times the change in height, right? And this is also applicable to gases as well. However, when the space is so large, and since the air is affected by pressure and temperature, therefore pressure variation across the atmosphere will be different. Okay, so again, we said that we have already derived this hydrostatic equation, which is applicable to both liquids and gases, as long as it's a static fluid. However, when the space is so large, and since the air is affected by the pressure and temperature, and therefore pressure variation across the atmosphere will be different. Okay, so to derive the equation, in this equation we have delta P is equal to negative the unit weight times the delta Y. Now, since this is air, then we'll be using the ideal gas law, which is PV is equal to mRT, where P is the pressure, V is the volume, and M is the mass, and R is the gas constant, and T is the temperature. Now, if we will write this, if you recall this, that this one is just simply negative rho G times delta Y, right? The unit weight is just simply the mass density times the gravity. Now, recall also that density is just simply the mass over volume, and we have mass and volume right here, and therefore if we rewrite this one, we have P over RT is equal to M over V, and this one is the density. Now let's substitute this density into this equation. Therefore what we get is P over RT times G times the delta Y. Okay, and this is our delta P. So now let's combine terms. Since this is pressure, this is also pressure, then therefore this is going to be delta P over P is equal to negative G over RT times delta Y. Right, so if we're going to derive it using the differential volume, then if we define this at a point, or pressure at a point, it's going to be dP all over P is equal to negative G or T times the differential of Y. Okay, so you would see here that the equation is no longer linear. It's no longer a linear variation with respect to elevation, and in fact, if we try to plot this out, it will look something like this, right? So we have this pressure, and then we have this Y. So Y, let's say this is the independent variable, and this one is the dependent variable. Then if you plot this out, it will look something like this: pressure over elevation. But if we flip this, because usually our Y is along the vertical direction, then it will do similarly, something like that. Okay, so it's no longer a linear variation in contrast to this hydrostatic equation. Okay, so I guess that's all for this topic about pressure variation in the atmosphere. You can read further informations about this in many fluid mechanics textbooks. Okay, so in the next video we'll be moving on to our next subtopic on pressure measurements and manometers. So see you in the next video.